And we're live from downtown Millbay. Are we live? Go. Connect. Yes, we are. Do we have a picture? 4, 5, 6, 7. Do we have a picture? Yeah, we should. There it is. Done. Julie, were you saying you don't have a copy of the actual reaction?
So no, just balance it, bro.
We had 1,000 of them. However, do we have 1,000 now? Yep. You're supposed to do them after today.
It's like the energy that is required to start a chain reaction.
Yeah.
Or just say reaction, kind of like a chain reaction.
Chain reaction.
Yo, throw that in the We're both equally right. I'm right. I'm right at this point.
Okay, who needs a copy of the sheet? Julian?
And Andrew
Yep. Yep.
Andrew's we got the rugby game tomorrow. I will beat you. Because I'm gonna have practice. And you don't know how to, you wanna know how to play.
Yeah, I've learned tomorrow to power cricket. The bases islands,
I got
it's on the mainland.
And I got like double
Like ham, mac and cheese bake.
Ham, mac and cheese.
No, so they are.
Ham and the mac and cheese. I don't know. Ham, mac and cheese bake, Caesar salad.
No,
Okay.
almost like no ham.
Sounds
Apologies for the
This is back.
delay. That's even worse, given that we don't want to be behind.
Why is it Caesar salad though?
Okay. The first thing that we're going to be looking at with reactions in terms of their energy change, we reflect reactions with a potential energy. Potential, and then that can go away. I'll just rotate that and make it smaller and put it there. Excellent. A potential energy graph. And we always talk about chemical energy being potential energy. Where actually is the energy for a molecule or ion? Yeah.
In the electron.
In the electrons. So it's in the actual bond. So when we're measuring their energy, we're measuring how strong or how much energy each particular bond has. For this particular reaction, where we're going an exothermic H2 plus O2 going to H2O, we're going to start something here. these bonds are high energy. H2 and O2 have high energy bonds. And then they go up. And I introduced last day with the gummy bear. What did I need to do to the gummy bear to get that reaction to go?
Let 'em.
You need to heat the bottom of the
I had to heat the flask. Because otherwise it wouldn't have this amount of energy to get over the amount of energy you needed to form new bonds. And then it comes all the way down.
Are we drawing this?
You are drawing that.
Oh,
Julie, oh, you can't use their seats as a footrest? What are you doing? Crazy person. This amount of energy the energy that from the beginning to the top of the peak there, that's the activation energy. That's the amount of energy you require just to start a reaction. For some cases that's high. This room is not currently on fire, unless I do something drastic right now. Because even though that cardboard would love to be on fire and would give off a ton of energy for doing so, the activation energy for that is much higher. If you've ever watched a movie in which they have, firefighters running around, they talk about flashover, and they make it really exciting. The reason that's a thing is that you can get the temperature of a house high enough that the air itself has enough energy to light everything on fire. And at that point, you don't need an ignition from one thing to another. At that point, everything's on fire. It has given the amount of activation energy needed, regardless. Also, we call this reaction progress. The bottom of these diagrams isn't time, because if it was time, then sometimes the reaction would happen, sometimes it wouldn't, and it would depend on how much energy was involved. We call reaction progress because we're assuming there's energy, what will happen as the reaction occurs. So it's just a way of fixing everything. So it's in place. It's a bit like instead of the time for your trip in which you actually go there and stop at gas stations, it's the Google outline of where you should go ahead of time. This is assuming everything goes perfectly. What type of reaction is this again?
Exothermic.
Exothermic.
So would an endothermic reaction then go not even up to the activation energy? Would it just go below?
Oh no, it will go if it does not get to the activation energy. The reaction will not go, but it for it to happen, it does have to go up. It looks different in a different way. Exothermic. Now, this is the energy that went in. Once again, where is the chemical? Where is the energy in molecules? Where is that potential energy located? Yes? Nope. Jojo, can you put away the laptop? Yep. In the electrons. In the, starts with B. Bonds. Bonds. Lots of bonds. I'm looking forward to the day that there's a Doctor Who James Bond crossover and we can have all the bonds in one film. Because that will make really good analogies for this. If this energy is going up, what must you be getting more of?
Bonds.
Pablo, go over there. Excellent. More bonds. So as you go up, we're making more bonds, or bonds formed. As we go down, if we're going down, what happens to those bonds? They break. So what that means is that energy, once you have your new bonds, it has to be released in some way. So these were high energy bonds. And I didn't seem to put the product over here. The product over here is H2O. And these are low energy bonds. And we lost, if I go keep going to there, and I take, let's do that in a different color. This, we started high and went low. We lost all of that energy. This is the energy to the environment. Get your question in a moment. Yes?
High and low energy bonds, are those synonymous with stable and not stable bonds?
Yes. A low energy bond is more stable. So a high energy bond can be really reactive. And if they're very, very reactive, they might, spontaneously just break. The most explosive compound we have ever made that we can actually make, it doesn't immediately fall apart. We actually can't measure the stability of its bonds because they're so unstable that bringing it to the special room, to the machine that measures that, it blows up. They have to make it in the lab, and the machine that measures that is like too expensive to do in the lab, so they can never bring it there. There's an institute in Germany that specializes in that, and it's a famous compound for that reason. There's a hand up about to be there. Yeah.
How do you know if those are high energy bonds?
We measure them. So, sorry. I just realized how unhelpful that answer was. We measure them compared to other things. So we know, for example, how much energy came out. So we know the difference between these bonds and those bonds. And then we can measure the energy in which, let's say we have O2 plus N2 goes to NH3. And it will have a change in energy as well. And it has oxygen in common. And then we'll measure other reactions by comparison that have nitrogen. And eventually we'll figure out how much that bond is and those bonds are. But we won't know them on an absolute scale. We'll know them on a relative scale. There and then there.
Do we write O2 plus N2?
No. That was just to illustrate a point.
Is it like, so there's not really a process for us, students?
No. I'd give you a diagram. Yeah. Or I would tell you it's exothermic and it's like I didn't put numbers on here, but in Chem 12 we put numbers on there and you would like, oh, it's plus 50 kilojoules or something. Oh, no. Oh yes, you don't even have to ask, you can just go and then come back provided your phone's in the thing. Yes.
What do we write in exothermic energy?
Oh, I hadn't found. So, where is that energy going? It was in the bond. Now it's out of the bond. Where did it go? To the environment. So, how did we see that energy with the gummy bear? Heat. So it's passed to the environment. So we got heat. What else did we get? Yeah. Light. Anything else? Sound. That was the screaming part. The mitochondria is the... Ooh, that was actually a little bit better than the other classes, the first one, but still not like oomph, really. The mitochondria is the... I don't think we had the back row joining in. The mitochondria is the... Excellent. There's even a song about the Golgi apparatus. You have long learned C6H12O6, which is sugar. And you take that with oxygen and you burn it to make CO2 plus H2O. And what else is in the mitochondria reaction? Plus energy. And they lie. Because yes, energy comes out, but you're not like a piston engine. We're not blowing something up like we're burning gasoline to make off CO2 and water, and then that moves a piston inside your body. It's mitochondria. So how do your cells get that energy? Now what you'll learn later on is that these are high energy bonds, and these are very low energy bonds. And then here you have high energy bonds again. Does anybody know the molecule that's made there? Plus ATP. And A stands for adenosine. It's not important. We'll just represent it by A with a circle. P stands for phosphate. And T stands for tri. So it has 3 phosphates. Now if you take biology, you'll find they'll draw them in a squiggly way. Because those energy bonds. So you don't just get the energy out of the burning reaction in your mitochondria as like heat. You actually make something that has high energy bonds. And this just floats around your cell. I'll get a question in a moment. And then let's say you want to pull, it's a muscle fiber cell, it wants to like contract. The ATP will then attach to a receptor and it will break that bond, and that energy will go to moving, like literally moving that particular muscle contraction. Or it's an enzyme, and the enzyme has to move in order to make the reaction happen more quickly as a catalyst. And so it'll attach an ATP, and the enzyme will move, and then it will make the reaction happen. So you are burning ATP. And all you do is you burn it down to ADP, adenosine diphosphate. And so this reaction is missing the other part. And you just continuously make energy. Because your cells need energy in a form it can use. Just like for years, decades, we had cars and we used gasoline because it was portable. You could put gas stations up. It was easy to put the energy there. It was something we could burn it everywhere. It was great. It was a wonderful invention. Just gave off way too much CO2, and now we have to deal with that. Mitochondria need something they can move around the cell. They can't move heat, but they can move a molecule. So you're just making molecules with mitochondria. That's the energy part of powerhouse of the cell. You can break it again, and then you get AMP, adenosine monophosphate. And if that happens, your body starts to freak out. Because why the heck are you needing so much energy? You're down to a single phosphate. And so that will kick off some reactions to put your body into an emergency mode. Question? Yes? Question, God?
Could you just draw out an energy change without all the words on the board so you know what we should be drawing?
No, I want you to draw the words too. Everything I've written down so far.
And every time we write that. Like when we're doing
No, right now. This is why want you to write down.
Would you be able to show us on the board what we do in an actual situation?
It would depend on the question. So if I ask you just to draw a exothermic reaction, you would just draw the exothermic reaction. If I asked you to label the energy change, then you would want to draw this one because that represents the energy change. I want you to draw the. So this is like a paragraph of notes in a drawing. You might be asked for different parts. Yes.
What does an endothermic reaction look like?
Oh, well, we're doing that next,
Okay.
and I'm going to physically show you one. Where did my pen go? I will find it in a moment. So products have now. Do these products have more or less energy in their bonds?
Less.
Less. They're low energy bonds, and that's why it's exothermic. And I think, although what I really got for your question was that diagram's really complicated, Mr. Dufeld. What is it? And I'm like, yeah, it kind of is. This, the energy to the environment, the energy change, that is known as delta H.
We write that in when we're doing it.
Yeah, it depends. I'm probably not going to ask you too much about delta H. It's something we do more of in Chem 11. But if you're aware of it now and you've seen it before, it helps you to talk about it, because then you can just say delta H instead of energy change. The H stands for heat, since heat is coming out or heat is going in. And it always measures it by where you come from. So we started with reactants and went to products, and energy came out. So the amount of energy dropped. So delta H is negative for exothermic reactions. And I probably will not ask you that. But it is something that you could mention if you wanted to impress. So, activation energy, energy to start the reaction. We have the delta H, or the enthalpy. I'm not going to write that one down. Delta H, energy changed. It went from high energy bonds to low energy bonds. That energy came out into the environment. We heard the gummy bear screaming, "No, no, please, no," as the other ones watched. And that's an exothermic reaction. No. Jillian, what's the other one called? Endothermic reaction. So that's where it takes in energy. So if, I'm just going to scroll to there. What would change in this diagram in order to take energy in? I've heard from you, I just asked you. I've heard from you several times. Haven't heard from you yet.
Activation energy would change.
If this was bigger, so let's just, don't write this down. Let's just try all the different things. If I made this bigger, oh my goodness, and I made 3 of them. If I made this bigger, or I made it smaller, does that change the amount of energy?
Yeah.
Which energy does it change?
Delta H.
How does it change the delta H?
Because there's less activation energy or more.
But where does delta H start? Does it go to the peak?
No, it starts at
No.
the start of the reaction.
It starts at the start of the reaction. So delta H, if this is our start of the reaction, it starts right there. The activation energy could be super high. Does that change the delta H?
No.
No. Yes? Oh, you sure?
I was just going to say that it changes the activation energy, right?
It does change the activation energy. So if I drew this high peak, that would probably slow the reaction. Like maybe I'd have to heat that stuff we heated for the gummy bear a lot harder to get it to go. But once it went, once you go this high, if you do get over it, you get all that energy back plus more. So if you have a really high activation energy, you might make it slow or hard to start, but once it goes, you're going to get it all back plus more. Yes?
Would there ever be a situation where you need to cool the initial product to be able to start the reaction?
No.
No?
Not in grade 10. The more complicated answer is no, but there's a related one about equilibrium and shifting a reaction to either side in which maybe. But heating a reaction always makes it go faster, so you almost always want it as high as you can get it. So what do we need to change on this to make it take in energy, absorb energy? Anderson, you went like that. You haven't answered the question. Julian, I hesitate to ask you because of the sound of your voice.
Well, we just like gains energy. So I can just like draw a line over there, like above the activation.
Above the activation.
Like, above like the green part, like on the purple line.
So where do I have to draw it? Let's pick a brand new color. I'm going to pick orange.
Instead of it like going down.
So-
maybe like a
So I start here. I'm going to keep the activation energy the same. Now what do I do?
like it doesn't go all the way down.
Doesn't go all the way down. Where does it go to?
If you look at it's more than when it started off.
It more than start off. Yeah, if you go like this, now it doesn't go down. Which direction does the arrow go? Oh, it now gained energy. So that's what an endothermic. You can have exactly the same activation energy. It's just you're not going to get it all back. Now, don't draw this on here because, like, first of all, it's a complicated diagram as it is. So let's delete that. Or Control Z, Control Z, Control Z, Control Z. Oh, there we go. No, keep going. normal. There we go. But on this one now, starting from here, draw in pencil, in case you make a mistake, what an endothermic reaction line would look like. And while you're doing that, I know you grabbed the demo, but I wish to show you. One thing we haven't done yet, fill in the blanks based on your knowledge from the previous page. Put the energy term on the correct side. Put an energy term in this one. Where does the energy term go? And draw the correct diagram. We'll correct in class, but see how much of that you can fill up.
This is endothermic.
Is it?
Yeah.
But I thought it would go down.
This has to be higher than where it's starting.
Oh shoot, I did it wrong.
Yeah, it takes in. So that this
Can I look it up, or is that
here to here, that's energy released.
wait, activation?
It absorbs.
So it starts here.
Yeah, okay.
Is it?
You're writing in the blank. We're writing on you.
I wanna
Yeah,
copy
that's the
it.
wrong side.
This is I did.
This is exothermic.
Just higher than this.
Wait. No, because it has to.
Activation.
Yeah, but it needs to give out energy.
No, you have more energy here and then it has less energy there.
Yeah, same with exothermic. No, exothermic gives out energy. Oh my god.
Wait, so they both energy?
No, I think just you think you're right.
What?
I think you're right.
More.
Is that right, Julian?
Because this is the low energy bond that we saw in the page, so it's high energy. So they're warm.
I believe you, Oliver. I feel like
I'm probably wrong, but
What's name?
but energy you get less, you get higher energy bond.
And she thought I was, yeah, because
it absorbs and wow.
No, it's because it's creating higher energy bonds. It starts to flow, energy high. So it gives
high energy bonds take up more.
yeah, it's like absorbs oxygen. Because this one, to get the low energy it has to release all the energy.
Pardon?
So then the opposite is what the gain energy.
Sue, I'm going to give you a sheet that has your grade, your proficiencies, and areas, what areas you might want to review, and I'll have a detailed. I did not put written in the copy.
I'm gonna look at my
I'm
key.
going to take a look at your
Yeah.
My advice is that you can make each. I don't know what I'm doing wrong. I'm super
Yeah. Put away. Endothermic diagram. There, yeah, close. I do say in pencil just so that, and then the endothermic, that one is exothermic. Because it looks the same as if you flip back to the other one. Looks the same as that one.
okay.
So if you're dropping down below where you
Wait,
started,
what'd you
you're
get?
getting off energy. Same with that one.
Never mind.
Absorb.
What do you
So
get
the
for
energy goes in the bonds,
I said at the bottom, A plus B equals AB plus A.
More. So it should end up higher.
Yeah.
So you put 1
Yes.
and put energy here.
Yes. That's endothermic. You're the one who just, sorry, exothermic. You're the one who just corrected it. That's also,
Well, no, because
No, but like, I just
I
can't
tried
use
to do EXO when we were doing the notes, but I do endo right here.
oh, I see. Did you turn over the page to the next section? Is this the second? Because this is just the endothermic diagram, that's all. Is this it? Yeah, you want to erase the bottom line, because that bottom line shouldn't be there. Yeah, that's there.
Where would delta H be?
Delta H is here.
Good. Good.
No.
Diane, are you okay? You need a little hump, because you need an activation energy too. So you should go down a little bit. as well.
Third?
Yes.
Oh.
Yes.
Oh,
Where? There.
no, it's not there.
I can never pronounce it.
Because if it's below, then that means it's giving off
Okay.
energy. This is endothermic. It absorbs.
Oh, you're right. Oh my God, you're right.
Okay,
Triangle.
as you're doing it, one, you still have activation energy, so it's still going to go up. I've made that kind of extreme. But it's also going to get absorbed into the bonds. So now we have activation energy. And if I keep doing this, what is the change in energy? What I would call the delta H. No, you already answered the last one. No, you've answered several. Yes. Yep, go. Pardon?
Like this, the bottom line to like the ending.
The bottom line to the ending point. So this is the delta H, and it's positive because it absorbed energy. Energy from environment. It absorbed energy from the environment. The products have more energy in their bonds. And this is endothermic. So where does the question? Yes. Where does the energy term go? On the reactants or the products? Did it give energy out or did it take energy in? Yes. Took energy in. So where does the energy term go? Where does the energy term go? Reactants or products? Reactants. So we would put energy here for this type because we added energy. If we go back to our exothermic reaction, we would add energy to the products because energy came out into the environment. Does that make sense? I saw a couple nod. Is there anyone with another question, or it doesn't make sense? That would be a better way of posing it. Okay. With this reaction, I added some energy to get it going, but then it just went on its own. Forests burn themselves. You light a match, the whole forest will burn down. But if you're making pancakes, pancakes don't cook themselves. You apply heat so it absorbs the energy, it creates bonds, and then you have a pancake. If you stop supplying the energy, the whole reaction just stops because that reaction requires a constant source of energy to go in. So most endothermic reactions just require constant heat for you to apply. It's not just the activation energy, they need to absorb energy just to go. There's a second fundamental force in the universe other than energy sides. And there are a few rare reactions that will go spontaneously. You don't have to supply the heat. but they're a bit like, you know how a fire is hot and you could actually cool yourself with this reaction. It's like a fire, but the opposite kind. Everything just gets cold.
Is it like one of those cold packs?
It's exactly like one of those cold packs. I'm going to show you a version of one of those in just a second. They don't use the same chemicals. Mine goes a little colder than they would go, and mine gives off sort of a bad smelling gas. But yeah, they have that kind of thing. So you break it, the reaction happens, everything gets cold.
You said like the energy it stays into the pancake when it's fried.
Yeah.
But what about when the pancake like gets cold and it loses all its energy?
No, you made the pancake.
Like
The energy was
like
absorbed.
the reaction's
It doesn't
over.
look like batter anymore.
Yeah, okay. You like take
The pancakes was batter.
Oh, I get
You
it.
put in energy. Now it looks like a pancake.
is there
That
any way to
it
take
transformed, and then it can get cool or hot or whatever. But the reaction has happened. Does that make sense? So it's not its current temperature. That is, I think, what you need. If you can now start working on the worksheet, I'm going to get the demo up and going.
Like the usual academic. I don't know if there's like a special. But then I think it's regular, so. Oh, yeah. You have to do that?
Excellent. Yep.
How do we write products and reactants, but we don't like show the reaction?
How do you what?
Because it says to write products and reactants.
Yeah.
Like, do we just say which part of the? I don't really know what I'm supposed to do. That.
I don't think I understand your question. Show me which one.
It says with the following labels.
Mm-hmm. Yeah. Oh, which side is the products? Always.
Or is that just? Is that
Right-hand
just
side.
Alright.
Is
I'll have to write it specific.
Yeah. No, products are always on the right. Reactants are always on the left. What?
Oh yeah, I read it wrong.
Hotter than I would.
No, because you have products on the wrong side.
I just looked at the word. I just looked at the word.
So complicated.
All the way back here. Whoops. Just as a review, when we do, hold it. That was actually in the previous one. Oh, here it is. We define reactants as on the left and products is on the right. We don't confuse you with other models until chemistry 12, when we tell you the arrow can go both ways. But in terms of nomenclature, when we write a reactions, it's always assumed reactants are on the left, products are on the right. So when you're labeling, reactants are always on the left, products are always on the right. And let's start weighing these up.
What's the relative energy
No. I write literally the capital letters N, R, G. When I write my own notes, like at university,
Getting quite
but there is
tedious.
no acceptable shorthand.
Alright.
Because you have to write it so many times in science, I developed my own ammonium thiocyanate.
Mr. Grisel,
Mm-hmm.
for question 1, are the answers just like the one underneath energy and reactions, that original graph that we drew?
I don't have the worksheet memorized, but the graphs, number 1 I think is just definitions.
Yeah.
And then number 2 you draw the graphs, and then I think for number 3 you start labeling the graphs.
Yeah, I'm wondering if the definitions are like
Yeah.
exothermic is gives off energy.
Yeah, things like that.
Okay.
Yeah.
Thank you.
Okay, I am turning on the snorkel. You hear the engine starting up. Okay. Move that off a little bit. And if I could get everybody to stand up, come forward. I would, in the old classroom, I would just do this in the class without a snorkel. But it is a little stinky, it gives off ammonia. A fairly rare reaction, because it also has 2 solids reaction, which is incredibly useful. However, it's a bit of a cheat, because water is embedded in one of the solids, and so that starts coming out of the solid. So keep a close eye on what happens. And everybody, you can come up, I've got a bag down there. Come up around where you can see. It's not, the particles are not odd, they're barium hydroxide, octahydrate, and thiocyanate. What's thiocyanate? Barium hydroxide. I washed the beakers. Oh, it does have some air, but I can smell the ammonia, so I'm gonna put it down a little lower.
Is it poisonous?
Ammonia?
Yeah.
Yeah, a little. I mean, you use it in cleaning compounds, the amount coming off wouldn't harm you. However, if you ever are working in, say, industry, and you smell ammonia, and then you stop smelling ammonia, run as fast as you can out of the building. Because it burns out your nostrils of the ability to smell it at about its lethal level. But normally you can smell it and people will leave long before it gets that bad because it is in fact so stinky. The danger with something like propane is that it's odorless, and so people will not know that they're in danger, and that's why they add that chemical to make propane smell. So, yeah, it's done quite a bit. We have attached to the point. Can't, as of yet, get it off. It is frozen. So this reaction is endothermic, feel the size. You'll also probably get a whiff of ammonia. Ammonia. It is cold, and it is forcing the reaction to occur by absorbing the heat out of the environment. In this case, the water I put down, it took, oh, did you get a chance to feel it? It is pretty cool. And so even now, off there. It has taken the heat out of the water has frozen, it's continuing to take heat out of the environment. So this is a bit like a fire, but the opposite. Whereas a fire will give off heat as it burns, this gives off cold, because it has to suck in heat. The reason why this endothermic reaction, though, is spontaneous is the second force in the universe is, as in many a young cartoon, I think it was a dragon in the second season of My Little Pony, is chaos. Chaos is a fundamental force in the universe. Everything gets messier and dirtier and more chaotic over time. You have to put in energy to reverse that. The products of this reaction, we started with two solids, which are relatively non-chaotic. The products are a gas and a liquid, and a large number of them. So the product is really chaotic, so that drags the energy, the reaction through. Now, it will slow down a bit as it gets a little colder, because reactions slow down when they're cold, but it keeps going, and it will keep going until all that's reacted, because of the gas being given off and the liquid being given off. So in this reaction, it's also an example of the forces of chaos, which I always thought was weird. Yeah, I can, it's stuck. So, that is your end of it. You may have a seat. Thank you. If you want to touch it again, feel free to do so. Don't put your finger inside of it. I want you to answer that question. Do you think you can drink it? Well, anything's drinkable once. I don't know for sure, but I do know I put in barium hydroxide, which is a very strong base like lye. So it would probably dissolve your throat.
So it would.
Maybe, yeah, depends on the amount. Pardon? Oh, because I'm a husband. That's where the photos go. Photos go. Hasn't picked his up. Oh. How many of you still need to finish up the lab? Is there anyone?
Oh, I don't
Okay.
need to do that.
So, there's another lab that also needs finishing up for another class. What I'm going to do is designate one day this week. It's probably going to be Wednesday. I do need to talk to all the classes. And of course, I won't see my other classes until tomorrow. But Wednesday lunch. If you're ill, drag yourself to that class, even if you miss all your other ones, because I can't, Miss Stewart won't keep the chemicals out forever. We need to put them away. So in order for you to make it up, that's going to be the last shot, Wednesday at lunch. So come then, if you need to finish up the lab, I'll have the chemicals out and ready to go for Wednesday. Okay? And in the last few moments of this class, I'm going to give you your other. Now that we're done reactions. 1, 2, 3, 4, 5. We're going to start with bonding and naming.
So thick.
Now I'm going to come around. I want to see your worksheet as I do so, the one you've just been working on. We've got the first page done. second page done.
Why do the electrons have different
Yes?
numbers?
Did I not give, oh, it's one person.
Because they're different metals.
This is weird.
I missed it.
It's like a whole story.
Worksheet?
Oh, so sad.
I wanted to see your worksheet as I go by. Pull your worksheet.
I already have this one.
No, pass that one along.
Oh,
But bring it, no, your worksheet, not your notes. Have your worksheet out, I'm gonna come around and take a look at what you're doing as you're working on it. It was handed at the very beginning of the class. There you go. You have to give it to me. And the other side. Excellent, I think you probably need more detail on there. Where's the worksheet?
Are we getting this?
Worksheet? Nope, not right now.
How do I know where to put these things?
From the diagram in class. So where are the reactants and where are the products? And go all the way to the beginning, because this is a review of reaction. Not this section. This side is reactant, that's an its own part.
But how do I know that there's stuff?
Oh, this is for a generic reaction.
Oh.
So a generic exothermic or endothermic reaction, you draw the diagram. Which side they're on is always going to be the same no matter what it is. We're not using actual numbers, so you're showing relative levels, not absolute.
Oh, okay. No, I thought we were talking about like acid.
Oh, that's, no, that's, I think you should.
That's why I was clear.
Oh, okay. Yes. There's a lot of reactions getting said. I mean, because that's not one reaction. Although related to reactions, you know what an enzyme is. It's a catalyst for its reactions in your body, and your body runs on enzymes. The reason you get a fever is because bacteria and viruses have evolved to infect you body. If your body raises your temperature, you have enzymes that are designed to work better at a higher temperature to fight them. And then the bacteria and viruses don't replicate as well because now it's the wrong temperature. So temperature is really important for some reactions. And so I can relate it to reactions in that way. But in terms of sickness and bacteria and viruses, so they're doing a ton of reactions. Yep, we did start, I was worried we didn't. Loud. In the last 7 minutes then, we're going to catch up. So if you can put away your worksheet now for review or finishing off later in prep. I didn't encounter someone in the last class who was like, I was like, where's your balancing worksheet? And they're like, oh, you didn't take it in afterwards, so I threw it away. I do expect everybody to have an organized 3-ring binder in which all your stuff goes in and you keep assignments and practice and notes in separate locations. And with that statement, I may be asking for your binder in to take a look at your executive planning at some point in the future. Just to give you a heads up. So, notes out. And on to this particular section. Why are you backing that away?
I thought you said for standard.
No, I said put the worksheet away. Not everything.
Wrong way.
Yeah. We are going to start off with naming. And in doing naming, we have to discuss ionic and covalent bonding because they're named differently. This particular diagram I picked. Now, I'm going to use some particular chemicals because we need to correct it. First of all, the diagram's completely wrong. But to make it simple, we're going to say it's lithium. Oh, well, these are transferring electrons, so giving away an electron in this particular case. So does that make this what kind of element?
Hydrogen.
It could. What kind of element? If it's giving away electrons.
Ion.
It is an ion. I heard cation. That's what it's going to be. But what kind of element? Hand, if you know. Yes. It's a metal. So on this side, we have metals. And then, if you have ionic bonding, what kind of element accept electrons? Non-metals. So on this side, we have non-metals. And to make things easy, I'm going to say it's lithium and fluorine in our example. So if we have lithium and we have fluorine, then I don't have to correct very much. Number one, how many electrons does lithium have total? 3. And how many valence electrons? 1. So it's going to give it away, which then makes sense. So this is correct for lithium. How many valence electrons does fluorine have? 7. So this is not correct. We need to correct that. So we've got 1, 2, 3, 4, 5, 6, 7. And given that that's what they did, I'll put little happy faces on them, which I don't know why your electrons need to have their own intelligence. It's a little weird, but okay. Also, I don't know why it's gendered. How do I know that that's the girl and that's the boy? Yeah, why did you have to do that? Do they have to have eyelashes? No. But they clearly felt a need, so I will give them both eyelashes just that we can have more. Also, once you notice it, it is so weird how often this happens. If you're looking at random like cartoons that are drawn for an educational purposes, or just like standalone cartoons, like just like stickers and stuff, the ones that they try to gender female often have their eyes closed, and the ones they try to gender male often have their eyes open. It's not a 100% rule, but it happens often enough that once I learned about it, I started noticing it everywhere. And the part that gets me is I don't know why. Why is that a thing? Anyway, there's lots of things that might be, but I don't know. Anyway, so now we have the correct number of electrons being transferred. We have lithium giving away its valence electrons to get a valence shell and giving it to fluorine. Fluorine's going to become -1, and now they're going to be attracted to each other for the rest of their lives because fluorine will be -1 and lithium will be +1, and they'll have that positive to negative attraction. That's ionic bonding. Ionic. We're going to have to do a little bit more work to correct this one. I also like how they didn't really know what to do for this one because they're not nearly as gendered. Like there's a little bit of eyelash there, but actually not that much. And there could be a little bit there. Maybe they're the same. We'll say they're the same. How many valence electrons? Now, it looks like they're sharing 2 electrons. So that's only 1 bond. What type of element does covalent bonding? Yes? 2 nonmetals. Can anybody pick 2 nonmetals that will make a single bond? Yes?
Sulfur. Oh wait, no.
Yeah, you might, if you get sulfur, you'll probably get into some double bonding, possibly. Yep. Fluorine and chlorine. So we'll make this one fluorine. Whoops. And we'll make this one hands, if you have a question or comment. Then that one chlorine. And how many valence electrons does fluorine have? 7. So we need to add some extra electrons. We've got 1, 2, 3, 4, 5, 6, 7. So we're only one off. And this one is, because you can see the third one in back. 1, 2, 3, 4, 5, 6, 7. And they each believe they have 8 because they're sharing one. Their bond will last forever based on mutual respect and sharing of responsibilities. Well done. Or maybe they're just friends and they're sharing a meal. I don't know. Work out the analogy on your own. Yes.
Do the ones on the table fit into the whole?
Yes, I assume so. Although it is weird that in their analogy they're also eating the clearly intelligent and aware electrons. I'm not, like at some point analogies break down. So this is covalent. It is sharing electrons. And I don't know how to spell that because I'm too ill. Sharing electrons. And for ionic, we are transferring electrons. Excellent. The last one, Pablo, where are you going? Why?
Because I gotta go really fast.
Why?
My bad.
What?
Because I got a meeting with PCH.
Not till class ends. You don't pack up until the bell goes.
Yeah, my bad.
Yeah, put it back, go back, go back. Because every time someone stops, you can say, you're going over, Mr. Neufeld, then I'll take a look at the time. But if everybody starts packing up and then you move, that disrupts the entire process. And I can't finish the last time. So. Yep. But now that we've interrupted, I have to spend more time talking about it to make sure it doesn't happen again. Okay? Yes, and then there's a question. For just before lunch, it ends at 1 o'clock. So you may pack up and go. We'll continue this next day. The worksheet is for homework. You're not going to have a quiz this week, but you will have some sort of assignment thing with it. Your next assessment on it will be on balancing and bonding.
Mr. Neufeld,
Yes.
can I take my lab book away?
Yeah. No, you can't take your lab book. You can't take your lab book. You can come into the lab on Wednesday. You cannot take it.
Are the grades posted on the zip code for last quiz?
You mean your test? Oh, they're not posted. They're there. I've seen them, but they're not posted.
I'm gonna be away on Wednesday, so I'm gonna miss anything important I should check on.
You're not taking your lab book. Sorry?
I'm gonna be away on Wednesday, so is there anything I should like?
Did you finish the lab?
Yeah.
Then you're good then. Yeah. So, I mean, yes, you'll miss stuff, but you'll have to catch up.
Will it just be the notes?
No, you're doing your stuff. Did you get all your observations in it?
Yeah, I already in Chinese.
That seems fair.
But you wrote it out all in Chinese. And then you translate. That seems like it would take a long time. Why don't you just write it in English in the first place?
There's not really
Enough time?
enough
Yeah.
time to write.
But that way you would learn English faster. You can come in on Wednesday. I'm not letting anybody take their lab book before then. Because I'm marking them as they are.
ISIS literally is taking forever to pick up.
Oh, there's no cell service in